All right, hello, welcome to AP Review 5. Today we're going to be talking about implicit differentiation, differential equations, and related topics there. A lot of it will be examples, and then you will really be digging into the homework to practice with this, but there'll be sometimes I'll ask you to stop and do some work, okay? Let's practice a little bit with implicit differentiation first. If natural log of 2x plus y is x plus 1, then what is dy dx? Now the first thing I see when I'm reading across this equation is that I have x's and y's that are mixed together on both sides. And that's one of our big cues that we have to use implicit differentiation. Implicit differentiation, here's maybe one way we could write about this. Sign that we need to use implicit differentiation problem when, let me adjust this, when our variable and I'm going to call it the with respect to variable, are mixed together. In other words, on the same side of the equation. My calculus teacher referred to, with respect to, she would just write out WRT, if you prefer that. Here's what I mean by that. I notice that I want to take the derivative of y with respect to x. When I look across this equation, I see some x things, and so the derivatives of x are just like normal, since that's our with respect to variable, but y is not our with respect to variable. It's the variable we're taking a derivative of, which we are assuming is a function of x. So when we get to y's, we're going to need to use our chain rule, because the derivative of y is going to be some function. I don't know what it is. So we'll call it dy dx. Okay, so let's go ahead and do this. Derivative natural log of blah is going to be 1 over blah. That's the rule for the natural log function. Times the derivative of the inside. So this is a chain rule. So times the derivative of the inside. Derivative 2x. X is our with respect to variable, so it's fine. Plus, but y is not our with respect to variable. Y is our main top variable there, okay? So the derivative of y, we can just call dy dx. It's 1 dy dx. Equals derivative of x is going to be 1, plus 1 is 0. Now we want to get dy dx by itself. So let me multiply 2x plus y, that quantity, to the other side. That'll give me 2 plus dy dx equals 2x plus y. I multiplied 2x plus y to the other side. I need dy dx by itself, so I want to subtract 2 to the other side. I will get dy dx is equal to 2x plus y minus 2. 2x plus y minus 2. Here we go. B. So implicit differentiation, be on the lookout for if that variable we're trying to take the derivative with respect to is not what we're actually looking at when we take a derivative, we need to use our chain rule and multiply by the derivative of that thing with respect to the variable. So the derivative of y with respect to x is dy dx. Okay? And then get dy dx by itself. There we go. There's a quick review of implicit differentiation. If you need more problems, let me know outside of what you'll have here, and I can get those to you. All right. Now, we also explored a lot of different topics around differential equations and solving differential equations. This was a major difficulty on the benchmark exam, so I want to spend some time with it. Which of the following is the solution to the differential equation? Now, first thing we got to remember, a solution to a differential equation is another equation. Okay, a solution to a differential equation is another equation. It is the equation that has that derivative and passes through the condition given. Notice this initial conditions on that original curve. So essentially we're looking for what is the original curve that passes through this point and has this derivative. Now our tool this year for solving differential equations was what we call separation of variables. Separation of variables. And separation of variables means we should be able to take a differential equation, an equation involving a derivative, and get all of one variable on the left, all of another variable on the right using multiplication and division. Those are the two operations we'll use, okay? Our initial condition here is x is 0, y is negative natural log of 4. So it's also important to remember and make sure you understand what the initial condition corresponds to. This is our x value, this is our y value, y of 0, y when x is 0. All right, so let's review how to do separation of variables using this equation here. Dy dx is going to be equal to e to the y plus x. So at first it may be difficult to say, well, how do I use multiplication or division to separate out my y's on one side, my x's on the other. I definitely want to get y's on the left because that's already in the numerator over here. And I can definitely see that I can multiply dx to the right to get it out of the denominator and up in my numerator area. But how to take care of the e to the y plus x is a little more challenging. But this is where exponent rules come in handy. E to the y plus x is the same thing as e to the y times e to the x, right? E to the y times e to the x. Because multiplying the same base, we would add the exponents. There we go. Now I can use division to move e to the y to the left side and multiplication to move dx to the right side. So let me divide by e to the y. So that's 1 over e to the y. dy will stay up in the numerator. I'm going to multiply dx to the right-hand side. That'll give me e to the x dx. Right? I divided by e to the y and multiplied by dx. Now, I got my variables separated. I need to try to get, remember, to the original equation. So that means I need an antiderivative. Some of these antiderivatives, like an antiderivative of e to the x, is really easy, but antiderivative of 1 over y, it's worth rearranging. 1 over e to the y is same thing as e to the negative y, right? E to the negative y dy. All right, so what's the antiderivative of e to the negative y? Well, the antiderivative of e to the blah is e to the blah, so it'll stay the same. But then I'm taking the antiderivative. So I'm going to divide by the derivative of the inside. The derivative of the inside, my exponent, is negative 1. So I'm going to divide by negative 1. Remember, you can always check this by taking the derivative. The derivative of negative e to the negative y would be negative e to the negative y times the derivative of the inside, which will give us a negative 1. Get rid of the negative in front and take us back to a positive e to the negative y. The antiderivative of e to the x is just e to the x. Technically, both of these have plus c's, but we gather them together on one side since we don't know what those c's are. So now I've taken my antiderivative. What do I do now? I've taken my antiderivative. My job now is to substitute in my initial condition, which is 0, negative natural log of 4, to solve for c. So this will be negative e to the y is negative natural log of 4, so it's e to the negative natural log of 4. The negatives will cancel out, and we'll have e to the natural log of 4 equals e to the 0 plus c. Well, e to the 0 is just 1. E to the natural log, those are inverse operations. Those will essentially get rid of each other, and we'll be left with negative 4. E equals e to 0, which is 1 plus c. So negative 5 equals c. I now know what c is. My job is now to get y by itself. Solving in this differential equation, we want to get y equals something. So I now know what c is. I have negative e to the negative y equals e to the x minus 5. Let me multiply negative 1 all the way through everything. That'll give me e to the negative y equals negative e to the x plus 5. Now I need to get to y, so let me take the natural log of both sides. The natural log of e to the negative y will cancel out the e, and we'll get negative y. But that'll leave me with the natural log of negative e to the x plus 5. Now I got negative y, so let me multiply that negative sign to the other side and get y equals negative natural log of negative e to the x plus 5. Okay. Negative natural log of negative e to the x plus 5. Do I see that anywhere over here? Yes, right here. So C is my answer. I separated my variables, got y's and x's together. Notice my y stayed in the numerator. I multiplied dx to the other side. That's almost always just going to be the pattern with these separable differential equations, okay? Make sure you use your multiplication division appropriately. Then I took my antiderivative, plugged in my initial condition, solved for C, and then solved for y. One other topic that we talked about when looking at implicit differentiation was Euler's method, using Euler's method to approximate solutions to differential equations. This is a really important idea, especially since this year it's only a 2 FRQ test, they're going to need to test BC topics. This might be one of them that's on there, so I would be ready for this. Euler's method is not necessarily hard, it's a little time consuming. I like to do it in the table method, which I'll show you again here. Let's consider this differential equation. Y prime is 2y plus 4, and let y equals fx be the particular solution to the differential equation, and we're given the initial condition 0, -1. All right. Use Euler's method starting at x equals 0 with a step size of 0.2 in order to attain an approximation of f of 0.4. So I'm going from 0 to 0.4. Looks like I'll do 2 steps to get up to 0.4, show all the work. Here's how I set up Euler's method. This is how I did it earlier this year too. We need to know our point. Where are we starting? That was kind of a not great looking line. So let's make this a little better. Nice. All right, there we go. We need to know the point where we start at. Making sure I get all the right ones, all the columns out here right. Okay. So we need to know the points where we're starting. We need to know what delta x is. We need to know what our dy dx is, our slope at that point. Then to find how much our y value estimation will change, we need to take that dy dx, multiply it by delta x. So essentially we multiply these two columns together to get the third column, and then we find our new x value by taking our old x value, adding delta x, taking our old y value, and adding our delta y. So what's our initial x and y value? It is 0, -1. So I copy that down here. What do I know delta x is? Delta x is 0.2. So what is dy dx at my point I'm approximating stuff at right now? Well, dy dx is 2y plus 4. So I got to plug in my y value. My y value is -1 at this point. So 2 times -1 is -2 plus 4. So my dy dx is going to be +2. There we go, +2. So what is my delta y? It's going to be 2 times, that's my slope, times how far I moved over, which is 0.2, which is going to give us 0.4. That's my delta y. So what's my new point? I take x, so that's 0, plus delta x, so that'd be 0.2. 0 plus 0.2 gives us 0.2, plus my y value, plus my delta y. So -1 plus 0.4 gives me, not sure why I put a plus sign there. My new x value is 0.2. I take -1, I add 0.4, will give me my new y value, so that'll be -0.6. So I've done one of my steps. Now I know my points I'm going to use to approximate stuff are 0.2 and -0.6. What's my delta x? It's still 0.2, that's not changed. But my dy dx is going to change based off of this new point here. So based off of this new point here, what does this mean for me? Well, y prime dy dx is going to be 2 times -0.6 times the y value of that new point plus 4. So I'm taking the y value and plugging it into my derivative equation because that's all my derivative needs. So what does this give us? 2 times -0.6 is -1.2, right? -1.2 plus 4, which is going to give us 2.8. So dy dx is 2.8. Then I multiply 0.2 times 2.8. What does that give me? Multiplying those things together would give me 0.56. So my new point, I'll take 0.2, my x value, I'll add my delta x, that'll give me 0.4. Then I take my old y value, which is -0.6. I'm going to add onto it my dy dx, how much my y value is going to change, which is 0.56. Now this point here will help me approximate f of 0.4. So f of 0.4 is going to be approximately -0.6 plus 0.56. You can just leave it like that, you don't have to simplify, but we do know that that would be equal to -0.04. Okay, so here's Euler's method for approximating solutions to differential equations, okay? I like the table method. If you find other methods that work for you, please go ahead and do that as well. So that's a quick review of our big topics around differential equations and implicit differentiation, but we need to be able to look out for these things really, really sharp, okay? So let me show you an FRQ that does several of these, assesses several of these topics in some more complex kind of ways. All right, I know we've seen this problem before, but it's a good one to look at to review these things. So we know at time t equals 0, boiled potato is taken from a pot on a stove and left to cool in a kitchen. The internal temperature of the potato is 91 degrees. At time t equals 0, sounds like an initial condition. And the internal temperature of the potato is greater than 27 degrees for all times t is greater than 0. The internal temperature of the potato at time t minutes can be modeled by the function h. And h satisfies this differential equation, where h of t is measured in degrees Celsius and h of 0 is 91. Lots of stuff going on here, but this last thing, it looks like we got a differential equation. It looks like we have some sort of initial condition here, right? An initial condition, h of 0 is 91. What does part A tell us? Write an equation for the line tangent to the graph of h at t equals 0. Then use this equation to approximate the internal temperature of the potato at t equals 3. Okay, well, we know how to write equations of tangent lines, right? We know for those things we need points, we need a point, and we need a slope. And we want to write the equation of the tangent line at t equals 0. So t equals 0. What do I know when t equals 0? Well, when t equals 0, h is 91. And that's actually one thing that makes this problem kind of confusing, that h of t is 91. So my point is 0, 91, where t is 0, and h, the internal temperature of my potato, is 91. Well, how do I find the slope then at that point? Slope, that's derivative. dh dt is negative 1/4 h minus 27. Huh. This is interesting. Usually when I have something like dy dx, I expect to see x over here. But this derivative is actually a function of h, the temperature of the potato. Not time, but h, the temperature of potato, is what this derivative will want to take. And that's something that made this question challenging. To get dh dt, the rate of change of the temperature, I actually need to plug in h, a temperature, not a time, but a temperature. So what do I know about where I'm writing this point? I'm writing this point when t is 0 and h is 91. So my slope is going to be negative 1/4 h, which is 91, minus 27, which is negative 1/4 6 times 64, which would be negative 16. So how do I write this equation? H is like my y value, t is like my x values. This is going to be, if we back up for a second, y, so h, minus y1, which is 91, my h minus h1 equals m, my slope, which is negative 16, x, which is really t here, minus t1. There is the equation of my tangent line. We could have also written this as, let's see, that's t minus 0, so that's just t, as h equals negative 16t, multiply those, and then add 91 over. Here we go. That's the equation of my tangent line. Now it says use this to approximate the internal temperature of the potato at t equals 3. So my approximation, h of 3, is going to be about negative 16 times 3 plus 91, whatever that comes out to be. I encourage you, don't simplify that, but if you do, you should be able to get it down to 43 degrees Celsius. Now we're starting to see some of the things that made this problem challenging. Our derivative takes h, not the with respect to variable, but h. All right, let's take a look at part B then, at part B. Use the second derivative to determine whether your answer in part A is an underestimate or overestimate of the internal temperature of the potato at t equals 3. So it sounds like first I need my second derivative. Sounds like first I need my second derivative. Okay. For B, well, I know my first derivative is here. So I'm not having to deal with parentheses and stuff. I'm just going to distribute the negative 1/4 in. So this will give me negative 1/4 h plus, it's going to be plus because it's going to be negative 1/4 times negative 27. So plus 27 fourths. There's my first derivative. I want the second derivative with respect to t. With respect to t. So what's that going to be equal to? D squared h over dt squared is going to be equal to negative 1/4 h. I need the derivative of this with respect to t, but h, that's not my with respect to variable. So all of a sudden, I'm in implicit differentiation. The derivative of negative 1/4 h is negative 1/4. Derivative of h with respect to t is going to be dh dt, right? Because h isn't my with respect to variable. The derivative of h with respect to t is its own function of time. The derivative of h then is dh dt, because h is its own function of time. Plus, the derivative of 27 fourths is 0. So what do I do with this? Do I know dh dt? I do. It's up here. I was actually given it. So what does that mean my second derivative is? My second derivative with respect to time is going to be negative 1/4. dh dt is negative 1/4 h minus 27. What does that mean? Well, I can distribute negative 1/4 times negative 1/4. That'll give me 1/16 times h minus 27. Did I say negative 1/16? I meant positive 1/16 if I said negative. Positive 1/16 times h minus 27. So here's my second derivative. And it says use this to determine if my estimate is an over or underestimate of the internal temperature of the potato at t equals 3. Well, in part A, I did a tangent line approximation. To figure out if a tangent line is going to be an over or under approximation, I need to know something about the concavity of my curve. If my curve is concave up, my tangent line will be an under approximation. If my concavity is concave down, my tangent line will be an over approximation. My second derivative talks to us about concavity. So what do I know? Well, in the problem, so my second derivative is a function of h. What do I know about h, the temperature of this potato? Well, h is greater than 27 for all t is greater than 0. Thus, so if h is greater than 27, this number, whatever it's going to be, has to be positive, right? So thus, the second derivative with respect to t is going to be greater than 0. And my estimate, I'm going to abbreviate some of this, my estimate in A is, and let's see, the second derivative is greater than 0, which means my h curve is concave up, which means my estimate is an underestimate. So my estimate in A is an underestimate of the temperature of the potato at t equals 3. Cool. This question's an implicit differentiation question. We had to take the derivative of h, but our with respect to variable is t, so we had to remember to do our derivative implicitly before moving ahead with our conclusions. All right. Let's take a look at part C now. Part C says for t is less than 10, an alternate model for the internal temperature of the potato at time t minutes is the function g that satisfies the differential equation given here, where g of t is measured in degrees Celsius and g of 0 is 91. That sounds like another initial condition. It happens to be the same values as the ones we were already working with. Find an expression for g of t. Based on this model was the internal temperature of the potato at time t equals 3. Now, they give us a differential equation. They give us an initial condition, but what they don't do, which they often do wording-wise, is they don't tell us find the solution. All they say is find an expression for g of t. But if I want g of t and I'm given a derivative, if I want to go from a derivative to an original function, I know I'm going to need separation of variables here. I need to solve this differential equation. Okay, to go from a derivative to an original, I need separation of variables to solve this differential equation. So let's do some of this. This derivative is negative g minus 27 to the 2/3. I need to separate variables. I see g stuff. There is no t stuff except for the dt. So I'm going to move the dt to the right by multiplying. That's normal. And I'm going to divide g minus 27 to the 2/3 to the left-hand side. I'm going to leave the negative sign just on my right-hand side. So I'm going to divide g minus 27 to the 2/3. I'm going to divide that quantity to the left, leaving the dg still there within the numerator. I'm going to multiply dt to the other side. That negative sign is still going to be there, so we can call it like -1 times dt. There we go. So I have my variable separated. Multiply dt to the other side, divided by my g quantity. Sort of our classic separation of variables move. Okay. I need my antiderivative. Antiderivative of 1 over g minus 27 to the 2/3. We got to keep in mind that this is really g minus 27 to the negative 2/3, right? That's the equivalent. So what's the antiderivative of this? The antiderivative of g minus 27 to negative 2/3. I would add 1 to the exponent. G minus 27, negative 2/3 plus 1. That's 3 over 3 will give us 1/3. Then I would divide by the new exponent. Divide by 1/3. Divide by 1/3 is multiplying by 3. It's going to be equal to -1. I need the antiderivative of -1. Antiderivative of -1 with respect to t will be negative t. The derivative of negative t will give us -1. Remember, you can always check by taking the derivative. Plus c. All right, we've done our antiderivatives. Now it's time to plug in our initial condition. Our initial condition is 0, 91, where t is 0, g is 91. So that'll be 3, 91 minus 27 to the 1/3 equals -0. So that'd be 0 plus c. 91 minus 27 is 64. The 1/3 power, that's the cube root of 64, is 4. 3 times 4 is 12 equals c. Okay, I'm going to drag this over here. I now know what c is, so I know 3 g minus 27 to the 1/3 is going to be equal to negative t plus 4. Because I know that c is now 4, right? I need to solve for g. That's my next goal. So let me divide everything by 3. That'll give me g minus 27 to the 1/3 equals negative t plus 4 over 3. Okay, I divided by 3. Now I got a 3rd power. That's a cube root. So to undo a cube root, I need to raise this to a 3rd power. So I'm going to raise this to a 3rd power. That'll give me g minus 27 is negative t plus 4 over 3 to the 3rd power. And then I'm going to add 27. So g is 27 plus negative t plus 4 over 3 to the 3rd power. And that is... Oh, I made a mistake, didn't I? I said a thing and then wrote another. Back up for a second. Always good to take track of yourself for a second. I said 4, but that's the inside here. 91 minus 27 is 64. The 3rd root of 64 is 4. 3 times 4 is 12. So C is 12. Ooh, good to catch your mistakes. There we go. That feels better. Okay. So we have our differential equation solved. Now we want to use this model to find the internal temperature of the potato at t equals 3. So g of 3 is going to be 27 plus negative 3 plus 12 over 3 to the 9th power, whatever that is going to give us. Oh, to the 9th power. Wow, I'm writing all kinds of things. To the 3rd power, whatever that's going to give us. You don't have to simplify. If you did, you would find 54 degrees Celsius. And there we go. This is one of those sort of more straightforward solving differential equations by separation of variables questions. Got to be on the lookout. It doesn't say find the solution. It says find an expression, but we're given a derivative and initial condition, so finding the original expression involves separation of variables. All right, let's take a look at one more. This next one I want just kind of lead us through. I want you to get a chance to kind of get dirty with it for a little bit and practice some, okay? Let's look at the next page. Let's consider this differential equation and let y be equal to f of x, and that's a particular solution to the differential equation with the initial condition 0, -1. Part A says, find the limit as x approaches 0 of f of x plus 1 over sine of x. All right. I want you to pause the video and give this one a shot. What tools have we learned so far this year that we could use to evaluate this limit? Try them out. Pause video, go for it. All right, let's take a look. So to evaluate a limit, we always first start by just plugging in. But if I plug in, what do I get? If I plug in, I would get f of 0 plus 1 over sine of 0. But sine of 0 is 0. What is f of 0? F of 0 is -1. So this would be 0 over 0, which is indeterminate. As soon as I see that, I know, hey, this is a L'Hopital's rule question. Hint, hint, if you see something set up like this, it's probably a L'Hopital's rule question anyways, if they're asking this to us on an FRQ. What does L'Hopital's rule say? Take the derivative of the top and bottom and try that limit again. So what's the derivative of f of x? It is f prime of x. What's the derivative of 1? It's 0, so it goes away. What's the derivative of sine of x? It's cosine of x. So we'll try this again. This limit is going to be equal to whatever f prime of 0 over cosine of 0 is. Cosine of 0 is 1. That's easy. What's f prime of 0? That's where I got to go to my derivative. Since y is f of x, dy dx, that's f prime up here. This is my derivative. So I need the derivative when x is 0. Well, when x is 0, f prime of x is 0, y is -1. So this is going to be -1 squared times 2 times 0 plus 2. That's going to be f prime of 0, because when x is 0, y is -1, so I got to plug all that into my derivative, and that's going to give me a value of 2. So my limit is 2. Not too bad, huh? Okay, let's take a look at part B. Part B says, use Euler's method starting at x equals 0 with 2 steps of equal size to approximate f of half. Okay, I want to start at x equals 0. I want 2 steps of equal size to get up to half. If I'm going to go 2 steps, equal size to get to half, each step has to be 1/4, right? Because 1/4 plus 1/4, that's 2 steps, gives me 1/2. If you ever get stuck, you can take the value you want to end at minus the value you want to start at, divided by how many steps you want. Give us 1/4 also. So our Euler's method table, we need that. Be a little quicker with this time. Go ahead and set up your table and try to use Euler's method to approximate f of half, okay? Pause the video, give it a shot, and come back to check your work. All right, here we go. So say I have a table, x comma y we need. We also need to know what delta x is. We also need to know what dy dx is. We also need to know what delta y is, which we know is equal to dy dx times the change in the x value. And then that'll give us our new points, which is x plus delta x and y plus delta y. Okay, so what's our initial point? We're starting at x equals 0, so our initial point is 0, -1. 0, -1. What's our delta x? Well, we already figured out that's going to be 1/4 if we're stepping twice to get to half. So what is dy dx? dy dx at this point, so I come back up here, I plug in 0, -1, which is actually what I already plugged in, so dy dx is 2. That means delta y is going to be equal to 2 times 1/4, which is 1/2. So my new point, x plus delta x, x plus 1/4 will give me 1/4. I mean 0 plus 1/4 will give me 1/4, comma y, which is -1, plus half will give me -1/2. Here's my new point. Okay. So I go again. What's my delta x? My delta x is 1/4. Now, what is my dy dx at this new point? That's a little more complicated. So I come up here. I got to find my dy dx at this new point just by calculating it again. So I know that my y value is negative half. That's going to be squared times the quantity 2 times. My x value is 1/4 plus 2. Negative half to the second power will be 1/4 times the quantity. That'll be 2/4. 2 times 1/4 is 2/4 plus 2 is same thing as 8/4. 8/4. 2/4 plus 8/4 gives us 10/4. So this is 1/4 times 10/4, which will give us 10/16. So my dy dx is 10/16, or I could simplify that and call that 5/8 if I want to. It's 5/8. So what's my delta y? How much is my y going to change based off this slope and my delta x? I multiply them together. 5/8 times 1/4 will give us 5/32, 30 seconds. So 1/4 plus my delta x, 1/4 will give me x equals half. That's where I want to end. Negative half plus 5/30 seconds is my ending y value. So f of half is going to be approximately negative half plus 5/30 seconds, that y value there. You can leave it there unsimplified. If you do want to simplify, you'll get negative 11/32. Okay, so last one, part C. Find y equals fx, the particular solution. So we want the particular solution to the differential equation with the initial condition given here, 0, -1. I want you to go ahead and try that. You have your differential equation up here. We know our initial condition. Try to solve this differential equation using separation of variables. Pause the video. And then come back and check your work. All right, here we go. dy dx is going to be equal to y squared 2x plus 2. I need to separate variables. As we've seen before, we'll multiply dx to the right. We'll divide by y squared to the left. So 1 over y squared dy. dy will stay over there. That's always the pattern. Equals quantity 2x plus 2. Multiplying dx to the right-hand side. dx to the right-hand side. Okay. So we have our variables separated. We need to take our antiderivatives now. 1 over y squared, that's not a natural log thing. Remember, 1 over y squared is the same thing as y to the -2. So the antiderivative of y to the -2, I would add 1 to the exponent. It's a power rule thing. And then divide by the new exponent. Divide by -1, so negative. Equals antiderivative of 2x with respect to x is x squared. Antiderivative of 2 with respect to x is 2x plus c. Okay. Now I can plug in my initial condition, which is 0, -1. So when x is 0, y is -1. So if y is -1, I have -1 to the negative first power, so that's -1, times negative, so it'll be +1 is going to be equal to 0 squared plus 0 plus c, so c equals 1 when I plug in my initial condition. Now I know that -y to the -1 is equal to x squared plus 2x plus 1. I need to get y by itself now, so I'm going to multiply -1 to everything. Y equals -1. That'll give me negative x squared minus 2x minus 1. Multiply negative through to everything, because I'm trying to get y by itself. Remember, y to the -1, that's the same thing as 1 over y. So if I want the reciprocal of that, if I want just y, that means I need to reciprocate this. Or I can just raise both sides to the negative first power. Is another way to think about it. 1 over negative x squared minus 2x minus 1. Cool. There we go. We solved this differential equation. Great. Hopefully this has been useful to go back and see some work with implicit differentiation, Euler's method, differential equations. We got to be on the lookout for all of these things. We got to try to hold all these complexities in our mind. What I'd like you to do, as we've done before, is now go ahead and try the practice problems. There are 3 more free response questions related to these topics. The second one's actually kind of challenging, so be careful with it. Do the best you can. 3 FRQs to do, and then I want you to watch the videos, score them, and then do your corrections and submit the score report as we've done before. Good luck, and I'll see you soon. Bye, everybody.